So in terms of the Doppler effect now, let's look at kind of real life experiences of it. So the first thing I'd like to point out is that frequency of a sound is directly, well, the pitch, I should say, the pitch of a musical note or a note is directly related to the frequency of the note. So the higher the frequency, the higher the pitch that you're going to hear. The lower the frequency, the lower the pitch. So if we take that in terms of an ambulance approaching us. So if an ambulance is approaching an observer, the ambulance is emitting a sound. Because the source is moving relative to the observer is going to hear a higher frequency than the frequency that's actually being emitted. And again, that's because the waves are catching up with themselves and hence bunching up, so he's seeing those wave fronts hitting him quicker than they actually are, with less time between them. So he will experience a high frequency note, in other words a high pitch note, as the ambulance approaches him, and as the ambulance moves away, now the sound that's being emitted by the ambulance, because it's moving away, so every time it emits a note it's further away, so the time between the wave fronts effectively is getting longer. So he hears a lower frequency, and in other words, a lower pitch. So hence when an ambulance passes by, you can hear a high pitch and then a low pitch. And if you think about it from the maths point of view, then the apparent frequency that he hears as it moves towards him is C times F, the actual frequency times the speed of the sound, divided by the speed of the sound plus or minus the speed of the source. Okay, V is the speed of the source. Actually, I don't think I said that in the last, when I explained the last equation. So C is the speed of the wave, V is the speed of the source. So remember, when it's going towards him, the frequency is higher. To get a higher value, this would need to be minus. When it's moving away from him, the apparent frequency that he hears is now lower. So it will be C plus V. Again, F is the actual frequency of the sound it's emitting. C is the speed of the sound. And V is the speed of the actual vehicle or the source. Okay. Right. Another example is in speed traps. Okay. So basically, a speed gun will emit a microwave. It's an electromagnetic wave. So it will emit a microwave towards a moving car. And that microwave will get reflected back off the car. Okay? Now, because the car is moving towards the observer being the speed gun, then those waves will get bunched up as the car moves towards it. So there will be a change in the frequency between the frequency that was emitted, the frequency of the microwave that was emitted, and the frequency of the microwave that is detected back in the echo. Microwaves are electromagnetic waves just like light. They just happen to be of a lower frequency. Okay? So speed traps radar are just another use of the Doppler effect, or a demonstration of the Doppler effect. If I was to just hold a buzzer that was making a sound and rotate that buzzer in a circle, and somebody was sitting here listening, again, they will hear a change in pitch due to the fact that the buzzer is moving towards them. Actually, it would be better to even rotate it this way, so that the buzzer is moving towards them and then away from them. Okay, and they will hear a change in frequency of that buzzer that's emitting the sound. Another one is what's known as red shift and blue shift. And basically, if you have a star, it doesn't really look like that, but if you have a star and you have the Earth and you have an observer on the Earth, if the observer is looking at the light that's coming from the star, okay, then the light from the star would be of a particular frequency. Now, the frequency of light is associated with the colour. So, going from red to violet, red colour is associated with the lowest frequency. We will do a lot more about this later. Violet is associated with the highest frequency. So, the frequency of light really determines its colour. Because stars are moving, and they discovered the stars are moving because of the shift in colour, if this star is moving away from the observer, then the frequency that the observer will see, remember when the source is moving away from the observer will experience a lower frequency than the actual frequency. So the light from the star will appear a different colour. It will appear a lower colour. So it will be shifted towards the lower frequency, and that is known as the red shift. However, if the star was moving towards the observer, then you would experience a shift in the opposite direction, because the frequency that the observer would be detecting will be a higher frequency, because the source is moving towards the observer. So when the source is moving towards the observer, you get what's called a blue shift. Don't know why they don't call it a violet shift. But remember, it's red, orange, yellow, green, blue, indigo, violet. So it's shifted towards the blue. Okay? And again, from that information, with calculations, you can detect the speed at which stars are moving away from us, and so on. Okay? I'll do a separate video now to do some of the examples on the Doppler effect questions.